Alrighty guys, so what we're going to do today is talk about photoelectric absorption, also called the photoelectric effect. Main things we're going to talk about are how it affects the image, what it is, when does it happen and what causes it, and what is the probability of it happening. Alright, so photoelectric absorption is an ionizing interaction that results when a photon is totally absorbed by an inner shell electron. Alright, and to show this, we're going to use this calcium atom right here. Okay, so already drawn a couple doodles on here. So basically, you have an incoming X-ray or incident photon comes in and it strikes an inner shell electron. Once it's knocked out, it becomes a photoelectron. So basically, this photoelectron results in an ionized atom with a positive charge. But luckily, it's immediately filled, and they sort of cascade in and fill in the spot. So every time that happens, we have new photons. Whoops, dropped my highlighter. Alright, so every time these electrons fill into the next shell, they release photons. The photons are released due to excess energy coming from the outer shell electrons. Alright, so moving on, we're going to look at how photoelectric interactions affect our images. So here we have like an extreme example of photoelectric. You could call it underexposed, but the correct term would probably be underpenetrated. Excuse my handwriting. I was always told I should have become a doctor. Okay, so like we learned in class, low kV equals high contrast and long scale shades of gray, and it results in lots of photoelectric interactions. High kV equals low contrast, a short scale, and more of the Compton interactions, or Compton scatter rather. So photoelectric is not necessarily a bad thing because an optimal balance of contrast is needed. Also important to remember is that plates and rods are going to be hard to penetrate regardless of how much kV that we use. It's just part of the image. Okay, so moving on, we will go to what causes photoelectric. So there are three important things to remember. Photon energy must be greater than the binding energy. So for this, a good example would be barium. So barium has an atomic number of 56 and a K-shell binding energy of 37 kiloelectron volts. So it would take a photon with the strength, or rather the energy, of at least 38 kiloelectron volts to be absorbed by the barium atom and also eject the inner shell electron. If a photon was any less than the binding energy, it could interact with the other shells, but not necessarily the inner shells. Just doesn't have enough energy. So the second important thing to remember is that incoming photon, gotta fix this real quick. Photons are more likely to interact if the kiloelectron volts is close to the K-shell kV. So a 40 kiloelectron volt photon is more likely to interact with barium, which has a 37 kiloelectron volt binding, than an 80 kiloelectron volt photon. Remember that as quality increases, photoelectron interactions decrease due to Compton and transmitted photons increasing. Photoelectric is much more likely to affect K-shell than the L-shell, and more likely to happen in higher atomic numbers, tissues, or objects. Alright, for example, a 40 kiloelectron volt photon is more likely to interact with barium, which has a kiloelectron volt binding of 37, than an 80 kiloelectron volt photon. Remember that as quality increases, photoelectric interactions decrease due to Compton and transmitted photons increasing. Photoelectric is much more likely to affect K-shell than an L-shell, and it's more likely to happen in a higher atomic number tissue or object. So that's part of the reason why that, here at number 3, as binding energy increases, so does the probability of photoelectric interactions. One way to express this is the formula photoelectron probability is equal to the atomic number to the third power. Simply put, more electrons can make more characteristic photons due to more shells and more electrons being available. And as the atomic number gets higher, it's also denser and it appears white on the radiograph, as we stated before. The outer shells have greater total energy, meaning they can release more energy when cascading due to the difference in the binding energy between the shells. So what does that mean? Alright, so we have a very important formula, and that is it's running out. The incident photon, or energy of the incident photon, is equal to the binding energy of the inner shell electron plus the kinetic energy of a photoelectron. Anyways, back to this formula for photoelectric. We already discussed how much energy it would take to knock out a K-shell electron. It would require, at least a little bit more than what the binding energy is. But just make sure you at least know this formula. Okay, sorry for the long video, guys. About ready to wrap things up here. Okay, so we have a calcium atom, which most likely be found in bone, with a 4.04 kiloelectron volt binding energy versus our tungsten atom right there. In the tube, would have characteristic spike at 69, and on the calcium atom, it'd be right around 4. But yeah, that about wraps things up.